All right, today we have our intro to Chapter 4, which is on probability. Section 4.1 will focus on just the basic concepts for probability. Event and sample space. An event is any collection of outcomes that is a subset of a sample space. We've already mentioned the sample space back in Chapter 3. Sample space is a collection of all possible outcomes. So, for example, consider flipping a coin. You pick tails as the coin is being flipped. What is the event? What is the sample space? Okay, the event is you picking tails. The sample space is tails or heads, because those are all the possible outcomes. Here's our definition for probability. The probability of an event E in the sample space of an experiment for which all outcomes are equally likely is, and this is the notation we use, probability of E equals the cardinality of the event over the cardinality of the sample space. So consider the following example. An experiment consists of rolling a pair of dice and noting the sum of the numbers. What is the probability that the sum is 4? First, let's consider the cardinal number of the sample space. In other words, how many total outcomes are there for this particular experiment? Well, each roll of a die produces 6 outcomes, so 2 dice will produce 36 outcomes. So the cardinal number S is 36. Now let's consider the cardinal number of the event that we want. In this case, there are 3 ways to get the sum of 4 with 2 die. You could get 1 and a 3, a 2 and a 2, or a 3 and a 1. So the cardinality of the event is 3. So based on the cardinal number of the sample space and the event, we plug these into our definition of probability, which is as follows, and we will get the probability of 4 is equal to the cardinality of the event of 4 over the cardinality of the sample space. So we replace those numbers with the values that we found, which is 3 over 36, or 1/12 when you reduce. That is the most basic example of probability that we can have. Now I want to emphasize that everything that we're doing in this chapter, I shouldn't say everything, but most everything that we're doing is based on counting. You have to be able to count the number of ways, which is why we did chapter 3. Now here are some of the axioms for probability functions. So let's say we have a probability of function that assigns a number of each event E to the sample space S. Following has to be true. The probability of E has to be between or equal to 0 and 1. The probability of the sample space happening is 1. In other words, the probability something actually happens is guaranteed. If we take a bunch of individual events, E1, E2, all the way through En, where N is pairwise disjoint events, then the probability of their sum will be equal to the probability of each individual event and then summed. Probability density function. The probability E is equal to the sum of the probability of the outcomes in E. Probability of nothing happening is 0. The probability of an event plus probability of the complement of the event is 1. And for any event E and F, the probability of E union F is equal to the probability of E plus the probability of F minus the probability of E intersect F. Notice that this equation is coming back. This is something from an earlier chapter, and it was actually our chapter on set theory. So again, this means the probability of the empty set, the probability that nothing happens, it's 0. So if there's an experiment, something has to happen. And this one here is basically saying, if I said what's the probability of, flipping a coin and getting tails plus the probability of flipping a coin and not getting tails, that's obviously equal to 1 because one of those two events is going to have to occur. Let's look at another example. A die is loaded such that any multiple of 3 is 3 times as likely as any other number. So if I get a 3, that's 3 times as likely as getting a 2. Or a 6 would be 3 times as likely as getting a 4. So what is the probability that the number 4 is noted on the roll of this die? Okay, so let's just go ahead and say 1 over x is equal to the probability that a number that is not a multiple of 3. So in other words, the probability of 1 is 1 over x. The probability of 2 is 1 over x. The probability of 4 is equal to 1 over x. And the probability of 5 is equal to 1 over x. Now notice that when we look at this particular diagram, so this right here represents the probability of 1, the probability of 2, now notice this is the probability of 3, so it's 3 times the other ones. Probability of 4, 5, and then here's the probability of 6. Again, it's 3 times as likely. And remember, based on our axioms, these 6 things that make up the sample space have to equal 1. So and they've got common denominators, we add them up. And so we get 10 over x equals 1. So x is equal to 10. Because 10 over 10 is 1. And since x is 10, we can substitute this back into the probability of 4, and we get the probability of 4 is equal to 1 over x, or in this case 1 over 10, or 0.10. So the probability of rolling 4 on this die is 1/10, not 1/6, which would be on a normal die. Let's look at another example. An urn contains 4 red balls, 7 black ones, and 12 green ones. What is the probability that you select a ball that is not black? So the cardinal number of the sample space is 23 because 4 plus 7 plus 12 is 23. Remember that the probability of an event plus the probability of the complement of that event has to equal 1. That's one of our axioms. Or if we wanted to, we could go ahead and subtract the probability of the event over, so we would get 1 minus the probability of the event is equal to the probability of the event complement. And one way to solve this is by using this above. This is called using the complement of the idea we're using here. So the probability of not black is equal to 1 minus the probability of black. Now you remember we've done problems like this back when we did Chapter 3 combinatorics, when I said, sometimes it's easier to find the number of ways to not do something than to actually do it. So it's kind of the same concept here. So the probability of not black is equal to 1 minus the cardinality of black divided by the cardinality of S. So we're going to get 1 minus 7 divided by 23. Now, how did I get 7? Well, guess how many black balls there were? There were 7. And so when we do 1 minus 7 over 23, you get 16 over 23. So the probability of not black is 16 over 23. Let's look at another example. Let's say that I tell you that the probability of A union B is equal to 0.84. The probability of A is 0.26. The probability of B is 0.72. What is the probability of A intersect B? So we're going to use that formula, which says the probability of E union F is equal to the probability of E plus the probability of F minus the probability of their intersection. And we're just going to do a little substitution into these values. So instead of union, we put 80 or 0.84 right here. And then we did the probability of E here and the probability of, actually this was A, I'm sorry. This is the probability of A union B, probability of A, probability of B, and then we're going to minus the probability of A intersect B, which we don't know, so we'll just leave that alone like it's a variable. So we combine the 0.26 and the 0.72, and then we subtract it over the other side. Now here's where a common mistake occurs. Notice that right here we have a minus and a minus and a minus, right? So when we subtract this 98 from over here, we do get a negative, and no, it's going to end up being positive, because if this side's negative and this side's negative, when you divide, you're going to get positive. So the probability of A intersect B is going to be equal to 0.14. Okay, last thing, and that's odds. Given an event E, the odds in favor of E are written in the form m to n, with m and n being natural numbers. So for probability of E, that will be equal to m plus, or divided by m plus n. Similarly, the odds against an event are written as n to m, and the probability of E complement will be equal to the probability of n divided by m plus n. Now I do want to stop here for just a second and make sure you guys know that the difference between odds and probability. Odds, like if I told you that the probability of something was, I'll just say the probability of A was equal to 1/2, it turns out the odds of A occurring are 1 to 1, because odds are defined as the cardinality of the event divided by the cardinality of not the event. I'm not sure if the book does a really good job of explaining that, but the probability is 1/2. The odds would be 1 to 1. So notice the denominator for odds is not the sample space. Okay, final example here. What are the odds of flipping a coin and having it land on tail side up? Well, it's going to be very easy because I just did it. There's one way to get tails. There's one way to not get tails. So m to n, the odds are 1 to 1. That's it.